So hello, my name is Mike Zephyr, and I'm an associate professor in the Faculty of Business and Economics at the University of Melbourne. And this is the Quantitative Methods Network, which is kind of an informal network that we have of, by, and for quantitative researchers here at the University of Melbourne. And today we're excited to have a talk by Jingjing Li, who is a professor at the National Centre for Social and Economic Modelling at the University of Canberra, or NATSEM at Canberra. Jingjing has degrees in both economics and computer science and is a board member of the International Microsimulation Association, or IMA. Jingjing, you've done a lot of work with a variety of government and non-governmental organizations and academic institutions, as well as think tanks worldwide, and you have more than a decade of experience in developing advanced economic simulation models, which are used to estimate the distributional and behavioral impact of policy interventions, for example, tax policy changes or environmental shocks like economic downturns. I don't know if anyone else thinks that might be relevant right now. You've developed a range of simulation and analytical software ranging from statistical add-ons for Stata and R, including the EDM package, which we'll be talking about today, as well as standalone policy simulation software in C and Python, and education simulation models as well. Probably most particularly, people would be aware of the STINMOD model, the taxation microsimulation model, which is actually accessible online through the NATSEM website. Is that true?
Yeah, it's on the website. Yeah,
that's right. Okay, cool. And today you're going to talk to us about empirical dynamic modeling, which is kind of a non-parametric, I'll let you say it, but kind of a non-parametric approach to characterizing and assessing causality in dynamical systems of some arbitrary degree of complexity. So thanks so much for doing this. We really appreciate it, and take it away.
Thank you, Mike. So today I'm going to talk about the EDM package we developed for empirical dynamic modeling in Stata. And this talk is loosely based on the paper we have. It's titled Beyond Linearity, Stability, Equilibrium, the EDM package for the empirical dynamic modeling and convergent cross-mapping in Stata. We can provide a link of the download of the working paper later after the talk. So I'm going to first start with talking about some challenges with the causal identifications, and then we're going to introduce the empirical dynamic modeling and some of the concepts associated with it. And then we're going to talk about implementation in Stata and some of the additional features we have in Stata for more advanced use case. And last but not least, we're talking some limitations about the approach and the implementations. So let's start with the causal identification. Causal identifications are fundamental underpinnings in many fields. So in economics, we are interested in knowing whether the reform actually has an impact on the outcome. In public health, we want to know whether the treatment or the medicine does actually improve the outcome of the patients. In psychology, we're probably interested in whether there's some sort of exogenous change in the environment, whether that actually influences the mood or not. Well, those things requires the causal identifications. And one of the ways to do that is to run experiments. So like things like the random control trials is considered a gold standard. However, those kind of things has some practical limitations because it has a very strict design requirement. We need to split people into two groups and those randomly assigned. And one of the group is subject to the treatment and the other group is subject to the placebo treatment. And then we compare the groups after the treatment to see whether there are any differences. In reality, that's a lot more complex. It's a bit hard actually to meet a stringent requirement of the design in some cases. For instance, if we do an evaluation on the cancer treatment, a type of a cancer treatment that designed to reduce the pain for the late stage cancer patients. And we can assign the patients randomly. However, only some patients will survive, and probably that's correlated to the treatment you give. And so even though the initial assignments are random, the data collection is not random anymore. That requires some sort of adjustments or some sort of a parametric assumptions behind it. And experiments takes time, and this is governed by, for instance, the cancer treatment that would governed by the chemical and biological process underneath it. And in the COVID vaccines, we talked about it, and it takes a long time in order for the vaccine to be verified that it's working or not working. Because of those design and the time components, the cost of running experiments is generally high, it involves people, and also involves a lot of ethical concerns. For instance, if you are interested in whether knowing secondhand smoking has an impact on children's cognitive functions, we can't just randomly assign children into different groups and subject them to the secondhand smoking. So a lot of the things, although we could have done any experiments to extract a causal relationship, it is very hard to do it in reality. So what most people would do is you use the observed data. The idea behind using the observed data is to exploit the observed variations in the data set. So hopefully we find some exogenous shock to one of the causes that we're interested in, and then we'll look at whether there are changes in the outcome variables. But that's not very easy because of virus endogeneity issues and also the specification things. So one of the statistical approaches, one of them is trying to mimic experiments. For instance, we're trying to use propensity score matching to construct a synthetic control group with a treatment group. However, even if we can construct the group, make sure the two groups look the same on the observed characteristics, it's very hard to make sure that those two groups actually are the same because of the unobserved characteristics. For instance, if we develop a job training program for unemployed, and the people who sign up for the program will be very different than the people who don't sign up for the program, not because of their age or gender, but could be the underlying motivations will be different. And another approach is to do with the difference in difference, where we just acknowledge that the treatment group is not the same as the control group. We just look at whether the difference between the two groups would change over time due to the treatment. And random RD, which is the regression discontinuity designs, even further relax that assumptions. We even think the outcome is too complex to be represented as a simple difference. We want the parametric specifications to see whether the coefficient has changed between and after the treatment. And all those things requires some sort of design and assumptions associated with it. And it can be very complex when the treatment is non-random and when the outcome correlates with the treatment in particular. And another way of doing these things, trying to identify the causal strands, is to incorporate additional information and assumptions. For instance, the instrumental variable approach, where we find an instrument that is supposed to be correlated with the causes that we're interested in, but not correlated with the outcome variables, at least not directly. And in that case, by using the statistical property of the instrument variables in order to extract the causal length. For instance, and if we want to evaluate this, the relationship between the number of crimes and the size of the police force, those two are obviously endogenous. One of the instruments we can potentially use is potentially an unexpected reform of the police force, which cuts the number of police or increase the number of police. And then because of this exogenous shock, we're trying to see whether there will be any changes on the other side. So those examples I gave are trying to refine the estimations in the observed variations, in the observed data. However, it doesn't really address the fundamentals that a lot of those causal relationships we have to know beforehand. We have to assume it goes one way or the other. Because that's not inferred in the data directly, it is actually inferred using the domain knowledge outside of the data itself. And another issue with that is the model specifications. Since all of those observed data parametric approach, what we observe is a correlation. It not necessarily imply the causation as we know. And also the lack of a correlation there may not necessarily means the lack of the causation. So I just put up a graph on the right-hand side of the slides. There are two samples drawn, and they're basically drawn from X and Y variables. And in sample one, those two are independently drawn between -1 and 1 is uniformly distributed for both variables, and they have a correlation of 0. And this is what you expect how it looks like when you plot them. And in sample 2, it's also a correlation 0, but we cannot say those two variables are independent. So this shows that actually the results will be very sensitive to the model specification, and the thing is we don't know the underlying data generation process, and the results will be very sensitive to the assumptions we put in. And in most cases, because we don't know how to specify a model, we put the linearity assumptions. And that may not necessarily be suitable for a more complex system. So in the examples in the graph, you see the relationship between X and Y actually changes depending on what the actual values are. They sometimes it's positive, sometimes it's negative. And so a linearity assumption here fails. We can see from the correlations that they're actually statistically zero, but well, actually there's a causal link underneath it. Another different approach is to use Granger causality to test the direction of the causality. But it has to involve some additional assumptions. The Granger causality determines whether there's a causal relationship by looking at the lagged observations of another variables, whether that one has incremental forecasting powers to the current VAR model. And the implicit assumption behind it is the information that contains by the other variables must be separable from the current VAR model. And that might be an issue in a more coupled system. The things are endogenous, and that means some of the information from the other variables will be bound to be captured by the variables you're looking at, and probably through the lag of it. Therefore, your estimations will be less reliable. And another thing is we have to formulate a linear specification of the models, hence putting in assumptions there, which may not always be appropriate. So what's the alternative? And one of the alternatives that has been developed relatively recently is called empirical dynamic modeling. The word empirical is referring that we're going to do these things based on the data without having to relying on some external assumptions of the domain knowledge. And the word dynamic involves is because we don't have to assume the relationship between variables are static. They don't have to be linear, and they can actually change over time, therefore the dynamic. So if you look at the, I hope you can see the mouse. If you look at this, this particular figure, and it's a butterfly attractors with 3 dimensions, X, Y, and Z. This is certainly not a linear system, and you can see the relationship are fairly complex. This is a common illustration of a dynamic system. And each of those things, each of the dimensions, we will be able to get a time series data. We can do that for X, we can do that for Y, and we can do that for Z. And the taken series, which is crucial for the empirical dynamic modeling, says that because the system is deterministic and they interact with each other, we must be able to recover the information of the entire system just from one time series. And how do we do that? What we can do is we can use the time series and the lag of a time series of a single dimension with a lag of tau, and another dimension with a 2 taus of the delay. And we plot each of these time series as a separate dimension. What you can get is something like this. And what you construct here with this lagged dimension, lagged plotting, is actually resembles to the original system. This is what we call a shadow manifold, and it shares many of the similar statistical properties of the original system. So you can see that they actually look same and they share the same topology. And what can we do with that constructed shadow manifold? And if we can do that for one variable, we can do that for another variable as well. So we can use variable X from that system to construct the manifold. We can also use the variable Y to construct the manifold. But they are not actually exactly the same. So we can use one of those variables, or one of the manifolds, to actually predict other variables in the system, because they, in theory, would contain the information of the dynamics. Same with the other manifold. However, because the X and Y's do not have a symmetric information footprint, for instance, if X causes Y, then Y must have some sort of information about X. And therefore, the manifold Y can be used to actually predict the value of X. On the other hand, if X and Y are completely independent, they are totally stochastic, then the manifold Y will not help us to actually predict the values of X, because those are stochastic. and it's not captured in those manifolds. Therefore, those relationships are not necessarily symmetric. And the asymmetries of the prediction powers from the one manifold to another when they do the cross mapping, it reveals the causality directions in this case. Another properties that we're going to explore is the convergent properties of the cross mapping. Because this manifold has a one-to-one mapping with each, the original system, this means that the denser the manifold, the more likely we'll be able to do the predictions, because the region will have a more denser information, so the prediction will be more accurate. If you have no information, very few information about that manifold, the prediction will not be reliable. So this is what's referring to the convergent property of the cross mapping. So the main advantage of this approach is we no longer need a parametric specification. We don't need to specify a regression with a particular models or have those specifications, because we rely on the shape of the manifold. We don't restrict the shape of the manifold, so they actually can represent the dynamics in any way we like. And so this naturally leads to the second point. It allows us to capture the complexities in the system. We're no longer bounded by the linear relationship between the variables. They can change over time. They can change conditional on the other variables, and those complex dynamics can be fully captured in the shape of the manifold. And because of the asymmetric prediction powers on the cross mapping, that can be also used to reveal the causality. So we can actually looking at the causality by looking at whether X has left a bigger footprint in the variable Y, or Y leaves a bigger footprint in the variable X. So now we know that can be done in principle, and how we actually do the projection, how we do the prediction using the manifold. The idea is, once we construct a manifold, if we want to do a prediction, for instance, on this particular red point, we find a number of neighbors around this point, and each of the points capturing a vector of the current state of that particular manifold, and also associated with the variables that you want to predict. For instance, we want to use the manifold of X to predict Y. And we can take the average value of the Y in the region, and that will to use that as a prediction. And this will be a local mean prediction. We want this to be local because we want this to be, we don't want to impose in terms of the structure of the global structure of the manifold. And we generally want this to be weighted because the closer the point to the prediction point, we want actually that particular observation information carries a higher weight. So if we do that, that becomes a simplex projection, and the weight is standardized, as you see that the further away from the initial prediction point, the smaller the weight it is. There's a minus sign here, so the smaller the weight is, the closer to the original point, the larger the weight becomes. And there's also one parameters we use in terms when assigning weight, which is a theta. A theta, in one way you can think about, is the strength of the nonlinearity, the degree of the nonlinearity in the system. If theta is 0, that means all the neighbor points are weighted equally. We're just taking a simple average mean. And if a theta is very high, that means the only point that is very close to the prediction point are taken into account. The one that are further away will not contribute much to the final prediction. So this is one way to do it. It's called a simplex projection. Another way to do it is called SMAP, which is short for the sequential locally weighted global linear mapping. The idea is similar. So we still find the nearest neighbors in the manifold. By exploring the property, those manifolds are actually resembles the original dynamic of the original system. Instead of taking a local mean, what we do is we run a local linear prediction. And it's similar to run a local regression. In a way, this is quite similar to a non-parametric regression you run locally. So in this case, we run a single vector decomposition to extract those coefficients. The reason why we run SVD instead of a local regression is there's a slight difference in the assumptions. In the regression, we typically assume there are potential measurement errors in the dependent variables, but not with the independent variables. And in our case, because the variable used for the construction which is the lag variables, are actually the same as the variables we use for the prediction, which is just the current variable, the future forward value of the current time series. We probably want to assume that the errors may exist both in the dependent and independent variables, which are both on the right-hand side and the left-hand side of the equation, so the SVD seems a bit more appropriate. And when we do the decomposition, we still want to weight the points differently. The closer the points to the prediction we want, the higher the weight it carries. And it's a very similar equation as in the simplex projection. We also have the theater parameters here. In the case of theater is 0, that means all points are weighted equally. So now we can do the prediction on the cross-matching. How do we evaluate the prediction accuracies? So we can use a number of different measures. One straightforward method we use is the correlation. If the prediction is perfect, we will have a correlation between the predicted value and the observed one is 1. Alternatively, some people don't like correlations for predictions. We can also use the mean absolute error, which measures the distance between the prediction and the observed values. And you can also come up with other measures to measure the prediction accuracy. You can construct an R-square measures. You can also construct MASE instead of MAE, or those kind of things. Regardless what measures you use, what you get is you'll be actually rank the prediction quality. And we can use that to compare the results from both directions when we use X to cross-map Y and we use Y to cross-map X. And the difference between the prediction quality, the accuracy will reveal the causal direction of the system. So now we know how to do that in principle, and it's how we actually do it in Stata. So we wrote a package in Stata which trying to automate most of the process we just described. And the basic syntax is just with a command called ADM, and then it's followed by another word, which is either explore or xmap, which is short for cross-mapping. And that determines the mode, how the ADM is running. In the explore mode, where we're interested is we're using the variable, the lag of the variables to predict the variable itself, while in the cross-mapping is we use one variable to predict another, which in this case is we need to specify at least 2 variables. And another parameters we commonly use is E, which determines the dimension of the system, as we described earlier. So the requirements of the ADM is the data set must be declared as either time series, which you use the tsset command to do that, or declared as a panel, which is the xtset command. And there are a bunch of other options you can use in order to refine the process. You can see that in the help file of the ADM. So how does it look like? If you have a time series data, for instance, it's X, and with a variable X there, if it's the type ADM explore X, what you get is output similar to this. And it will say, it will by default use an E of 2, and it will also report the theta, which determines the weighting, the weights of the observations, and that's by default is 1. And it reports the mapping, the prediction accuracy, both in terms of correlation and the mean absolute error. And by default, the Explorer mode uses a 50-50 split, which means once the manifold is constructed, we actually remove 50% of the points in the manifold. And we use this reduced manifold to predict the other 50%, which we actually observe. We know the real predicted value of those. Observe the values of the other 50%, and we look at the prediction accuracy. And in this case, it's very high, 0.999. Okay, so this is the basic format of the output. Now I'm going to give a bit more complex example with a logistic map. So here I'm trying to set up a system that has a typical chaotic behaviors, which means it's hard to predict. And it looks very random, the movement. So here is the time series of X is basically a function of its lagged value in this nonlinear way. And the variable yt is also a function of its lagged value, but also is influenced by the lagged value of X. And this is a deterministic system, so we want the first few observations to be burned to allow the dynamics to mature. So we basically remove the first 300 observations. And the code to reconstruct this dynamics is available here. If you copy paste this to Stata, you'll be able to reconstruct the data we use in the working paper. So how do they look like? So we start with a value, for instance, 0.2, and then if we let it run, you see a value oscillating between, essentially between 0 and 1, going back and forth. At the beginning is fairly regular, and after a while it starts to get messy. And if you introduce another variables, and those relationships are start to get quite complex. Sometimes they actually go in the same direction, sometimes they go in the opposite direction, depending on where you look at. And then we discard the first step, 300 observations, just to make sure the dynamics is mature, so we can do the analysis. Now we do a simple analysis on the correlation between X and Y. What we can see is X and Y is weakly positive correlated. It's not really significant at 5% significance level. And if you run a regression, you get something similar. You just show that those two variables are weakly positively correlated, but it's not significant. And you can see the R squared is extremely low. It's less than 0.02, shows that actually a linear prediction will be very poor in explaining the variations between X and Y. The first thing we need to do in analyzing a system like that is to determine the dimensionality of the system. As you might recall at the beginning, talk about reconstructing the system using the time series data. So we need to know how many dimensions that the system has. And we can approximate that by the prediction accuracy using the property of the reconstruction. So if we think about it, if we actually underestimate the number of dimensions, the reconstruction quantity is bound to be poor because we're actually not reflecting the underlying system. As we're actually getting closer to the real number of dimensions, our prediction accuracy would improve because it's getting closer and closer to the original system. However, if we overspecify the number of dimensions, and we're actually introducing extra numbers into the dimensionality, that means the density of the manifold would drop. With less and less dense information, the prediction accuracy would also drop. Therefore, we can actually, by looking at the prediction accuracy, to find out what the number of the dimensionality would be in the system. We can do that with a simplex projection with the explore subcommand using the range of dimensions specified in the E options. So what we can do is we run a command called, say, EDM explore, a variable we're interested in, and then we specify the number of dimensions we want to try. This is basically we're trying from 2 to 10. And we also use rep 50, which is short for replicate the result 50 times. As you remember, we're doing a 50-50 split in order to test the prediction accuracy. This would just repeat that process 50 times in order to get a more stable result. And what you get is something similar to this. So each row would have the dimensions that we tried, E equals to 2 versus E equals to 10, all the way to 10. And we have the prediction accuracy on average. And the result is the average of the 50 runs. We also report the standard deviation of the 50 runs. And in our case, we know that the system is constructed from only 2 equations. So we know the optimal E is 2. And we can see that as we actually introduce a higher E, the prediction quantities will deteriorate. And the more we introduce, actually, the less stable it is and deteriorate further. So now we know this is a system with embedded 2 dimensions. And we want to know whether this actually EDM is appropriate in the sense that whether the system is indeed nonlinear. What we can do is we use the SMAP algorithm to do that with the help of the theater parameters we talked earlier. So if we run an EDM Explorer, we know that the system has 2 dimensions. So we specify the E equals to 2, and we specify the algorithm we want to use is SMAP. By default, it uses simplex. And now we want to try a number of a theater. Here is trying from 0 to 5 with an increment of 0.01, which means we try about 501 theater values here. And K determines the number of neighbors we use. And if you specify 5, for instance, you would just use 5 neighbors in order to run the prediction. And if you specify a negative number, you will use all the possible observations to run it. And this reflects the nonlinearity very well. So what you get is an output similar to that, and it reports what the actual E used, what's the theta value, and what the rho value is, which is the correlations between predicted and the observed values. And if we plot this in a line chart, this is what we see. When theta is 0, which we actually assume the system is globally linear, and which compare with the theta is a relatively high value, which means we assume that the system is highly nonlinear. And you can see the difference in the prediction. The prediction quality improves as the theta goes higher, implying the system is nonlinear. Now we know the system has a dimension of 2, and know the system is nonlinear. Now what can we do about it? How can we use that information to infer the causal directions? Now this refers to a technique mode we use, which is the X-map, short for cross-mapping. Now we know the system has 2 dimensions. Now we can do the cross-mapping using the ADM X-map, XY we specified. This is 2 dimensions we use. And here is an output we have. So it reports the 2 results from the 2 mappings. The first mapping here reported is comparing the observed value of Y with the predicted value of Y constructed from using the constructed manifold from variable X. And the second one is the predicted value of X versus the observed value of X versus predicted value of X using the manifold constructed from variable Y. And in both cases, we actually use all observations available, that is up to 150 points in the manifold. We see a quite big difference in terms of the prediction accuracy. And so this means that the manifold of X does not have that much information about Y, but the manifold of Y has a lot of information about X, therefore it does a better prediction. And this infers the causal direction is more likely that X causes Y. And remember we talked earlier, so we're talking about if this is true, we will actually observe a convergent property. So how do we test that using the package? So what we can specify here is to add additional parameters, which the library size, which controls the number of points we use in the manifold. And here we specify start from 5 and all the way goes to 150. And we're gonna repeat each of the estimation 10 times, and you get a progress. We have 20 times in total because it's 10 for each direction. Now you will have something like this. You will have the mean of the prediction accuracies and gradually changes as the library size change. So how does it look like when we plot it? So if you just run it once with a library size of 5, I think here, yeah, so you get a row of close to 0, and in both directions, it doesn't tell you much. And if you run it a few times more and increase in size of the L, you start actually seeing there might be some patterns emerging. If we continue to let it to run and to run through the whole observation, whole data set we have, which has only 150 points, you see clear differences between the cross-mapping quantities. And the cross-mappings using the manifold of Y to predict X consistently perform superior compared with the other directions, indicating that's the possible causal direction is X causes Y. And the convergence is relatively rapid. You see that actually they start to be consistent after only less than 50 points in the manifold. And so how do we actually formally test whether there's a convergence? There are different ways of doing it. One of the ways we can do is we can fit in parametric equations of the convergence as long as you have some sort of a parametric specification saying, like for instance, like we're using the alpha times the E minus of the library size, it will eventually converge to alpha. However, that may not work in all cases because with different data sets, your convergence profile may look slightly different. Therefore, your parametric assumptions may not always fit. However, that's just one possibility. Another way is more traditional. We can do some hypothesis testing to test whether the prediction accuracy at the library size, say 100, is greater than 50, and prediction in one direction at particular library length is greater than another. And we can run some statistic tests, run a t-test on that to actually verify that. And another way is to examine the convergence profile with null distributions. And so, as you might notice, the convergence, eventually they would actually show there are very little variations at the end, because if we use all the informations, those the calculation of the cross mapping is deterministic. That means they are numerically bound to be different. So want to see whether actually that still happens when we have the randomized timestamp to see whether we have the same convergence profile. If we do, that means actually our current convergence may not be a reliable indicator that there is a causal relationship. So start with the hypothesis testings. We can do that with the t-test. We can run an ADM cross-map with two variables. We have a library size here, 140. We run it 100 times. We save the output and save the row values into a variable. We do the same with the variable like 10 with the 10 with a library size of only 10, and we can test whether the mean values are actually the same. And here this is straightforward a t-test. We can reject the hypothesis actually they are the same. And in this case, we know that the cross-mapping accuracy is at with a library size of 140 is much greater than with a library size of 10. And the other one is the new distribution comparison. This is how it looks like in the original cross-convergence profiles. And this is what happens if you randomize a timestamp, essentially creating placebo data. You see that the increase is obviously it's not quite there. And they do eventually diverge at the end because, as we talked earlier, the numeric difference was still present. However, you don't really see a consistent profiles, especially around the L at say between 50 to 100, which the trend is very clear in the original profile, but doesn't exist in the placebo. Now we give a real life examples using the Chicago data. And so we have a data set which records the number of crimes took place in Chicago and the temperature at the same time. And if you plot them, this is what you get in a scatter plot. This is in Fahrenheit. So you have to see there seems to be a positive correlations between that. We know that the number of a crime will not cause the change in temperature. So we know the causal direction is only one way. But this is based on our domain knowledge or contextual knowledge to determine that. Now we see whether we can actually find out that the causal direction using EDM. So we do the similar step as we did with that synthetic data set demonstrated earlier. And this is how the convergence profile looks like. And the red one is we use the number of crimes to predict temperature, while the blue one is we use the temperature to predict crime. And this is the correlation. And this line is the raw correlations between the data. And we can see that it is it's a clear this convergence to a much higher values compared with the opposite direction, and indicating that temperature is a causal driver to the crime. So what we covered so far is some of the basic features of the command, and we quickly talk about some of the additional features that we are building into the command, or some of the variations we can use. And first, we have some convenience features which allows you to standardize the variables by having a prefix z dot. And we also support all time series operators in Stata. That means we can take the first difference of the value of x using a d dot something. We take the lag of the x, we take the forward value of the x, or we take the lag of the second difference of the x. These are all supported, so we can run the command like ADM explorer z.x to give you the results based on the standardized measures. We standardize that to mean 0 with a standard deviation of 1. And you can do that with cross-mapping as well. Besides the default 50-50 splits, we can actually have more refined control to how you want to do the predictions. And one of the ways to do that is using a k-fold cross-validation. The k-fold cross-validation means that we use part of the data reserved for the prediction and the rest of the data used for constructing the manifold. And we use this part in the 5-fold cross-validation. We use this part in order to predict this part of the data, and we repeat this again and try to predict the second block, and third block, fourth block, and fifth block. That's the cross-validation. You can specify the options as cross-5, and if you type in the detail, you will report every single result as an individual line, otherwise you get a summary result. And dot 0 here is just suppressing the dot that will show by default. And here is the prediction accuracies in each of the 5 cross-validations within the cross-validations. Another thing worth mentioning is the multivariate embedding. So it is possible to customize embedding the specification in EDM. So by default, we're using a lag to construct embedding. However, it is also possible to construct multivariate embeddings in the sense that you're not only using the lags of one particular variables, and you can actually use 2 time series or even more time series to construct the embeddings. And in this particular case, we use the option called extra, which allows you to add additional variables into the embeddings, which will add on top of the existing lag of the system. Another thing worth mentioning is the extracting the marginal effect using SMAP. So one major difference between the SMAP and the simplex projection, although they are all locally sensitive, SMAP would allow you to extract the coefficient at local level, which means we actually can use that approximated marginal effect. And in this case, if you specify the variable save SMAP beta, this is the name you specify, and you will get a set of variables that stores the coefficient of the S-mapping. Instead of in the traditional regression, you get 1 coefficient, you get actually 1 coefficient per observation, because the coefficient is sensitive to the local state of that particular observation. So in this case, we have 7 dimensions, so we have 7 coefficient pairs and also another constant that is used. And you can plot the coefficient. And the interpretation is no longer about the lag variables. The intervention will be, we use actually all the other variables to control for the current state of the system, and we approximate the marginal effect of one of those coefficients. Another thing is the panel data. So although the examples we gave so far are time series data, but ADM supports panel data as well, as long as you declare the data set as XD set. So by default, it uses a pool approach, which means assuming that all the individual time series will share the same dynamic. So they all put together. It's as if we run a pooled regression. However, you can also pre-process data to obtain a fixed effect like estimators. You can demean the data just like this. You remove the mean, and what you can get is essentially you have a pooled common manifold, and then you have a difference with the mean with a difference at each entity. For each entity, that's essentially a fixed effect you have for each entity. Another thing I want to mention is the conditional causality. I want to remember that the estimates from the EDM reflects the overall bivariate causality. So it's basically saying overall combining all the possible routes and all the possible related variables, how much of the information of X would actually travel to Y to determine Y. However, not all causalities are direct. This is possible you have something like this. An X doesn't really causes Y, at least not directly, but all the causation are actually through another variable. For instance, here is Z. It is sometimes too useful to estimate the conditional causality rather than the overall causality as reflected in the EDM. And this approach is called partial cross-mapping, which is actually a relatively new article from Learn in this year. So we can also do that using our package. So in normal cross-map, what they care is about the correlations between the observed X and the reconstructed X using the manifold of Y. And in partial cross-mapping, we still want to compare these two, but we want to conditional on how the actual information travels through this path, which is we use the manifold of Y to predict X, and we use that prediction to predict X, and conditional on this potential link, and what's actually the direct causal, what's the causal strength between X and the reconstructed X using the manifold of Y. This is the partial correlation, which you can just plug in the formulas to obtain it. So how do we do Stata? In Stata, the cross-mapping, you can do it in this way. So you can do a cross-map, you specify one way in which we only want one direction, and we can run the predictions of X, predicted X using the manifold of Y, and we do the correlations of X and the predicted value. That will give you the row value as reported in ADM. And in the partial cross-mapping, we need to do that one step more to actually to cross-map to Z, and use that variable to cross-map to X. And we can run the partial correlations to extract the relationship between X and X underscore MY conditional on this particular path, the correlations, the cross-mapping results in this particular direction. Another way to review the relationship between multiple variables is through the time-delayed causalities. So the command also supports reverse and forward lag analysis with minimum change by using just the add a lag operator or forward operator. What we're exploring here is the direct relationship would actually have higher, and also they will actually be more recent. The indirect relationship, because of the time delay, would only reflect it with a greater number of lag. In this case, we have three variables, X, Y, and Z. The relationship between X, Y is direct. The relationship between Y and Z is direct. However, the relationship between X and Z is through that. So you can actually see this is the red line. The X and Z, actually the prediction quantity will be worse and also has a delay compared with the prediction of the direct mapping. So far I give a quite long overview about our package, and also want to remind people that the limitations, that the approach, and also the implementation. And the first thing is what we extract out of the empirical dynamic model through the convergent cross-mapping is the variance overall causality. So it thus covers the other possible passes of causalities rather than not necessarily the direct causality. And the second thing is the SMH is sensitive to the hyperparameters. It may not be that sensitive, but it would change due to the different hyperparameters used. And hyperparameters in here includes the theta, how you actually locate the weight, and also the other settings in your estimations. Another thing worth keeping in mind is the estimation might be slow because this is a non-parametric method, especially with the data set with a large n times t. So for the time series, so the example we use for the Chicago crime data is about 4,000 or 5,000 data points, which you can still get a result in seconds to a few minutes. But if you have, say, 100 times larger than that, it will take a significant larger time if you want to get a result. We're currently working on it to speed up the process. We're partnering with MDAP to look at a multi-core version of the plugin and potentially have the GPU version, or even potentially offload some of the computation to the cloud server so that to speed up the calculation. Another limitations, one should be aware of this potential with the missing values. So because we use lag values in order to construct the embeddings, so if you have a missing value in any one of the values in the vector, we have to throw away the entire vector, which actually may contain some information that you would want to preserve. There are different solutions to that problem. It's also actually part of the current research what we're doing. And we are trying to use a different approximation of the distance, or we're doing some sort of imputations, or we're doing change the shape of change of the specification of the manifold to allow for the missing values to be incorporated directly. Last thing is the current ADM command is designed with a continuous variable in mind. We want the manifold to be smooth. And however, that's not necessarily the case for all data types that we encounter, especially in social science. So there probably are different distance measures or some sort of adjustment might be needed if you want to use ADM on those data. So losses is the reference for the paper. And if you're interested in using the ADM, you can just install it in Stata, type in the SSC, install ADM. That will give you the latest version published on the SSC archive. Thank you. So, thank you.
That was great, Jing. Thanks so much. Let's open it up for questions.
I should probably back the screen back. Yeah.
Ask one question, probably a quick one. Yoshi Kashima is my name, from Melbourne University. If you have a case of something like a third variable as a cause that's producing the effects in, let's say, X and Y. So Z is the cause, and the X and Y are both actually effects. And would you be able to detect that kind of a situation?
Right. So in case you have three variables, X and Y and Z,
yeah.
And you said Z is the one actually causing it, both variables X and Y. You can actually cross-map X and Z and Y and Z, and that will easily review, that will have the strongest causal link there. And X and Y will be indirect link. As you saw in the one of the graphs I showed was the time delay. You see it actually a lot weaker. So you should be able to reconstruct the relationship between those variables.
Yeah, and if you don't know what that Z is, though, would you be able to tell that there may be a third variable there somewhere?
All right, that's a very good point. If you don't have the data, you don't know whether the Z exists. What you can, the only thing you can do is infer from the contextual knowledge.
Yeah.
So as I said, we capture the overall causal direction, but it may not be necessarily direct.
But sorry, go ahead. But I was just going to add to that, if I may, that in the case that X and Y are not causally related themselves, they're being driven by a third variable Z, then even if one can predict the other, you should not observe convergence. So that convergence criterion is the one that we use for making the causal inference, which is a criterion that exists kind of independently of the predictability of one time series or one variable from another. So as you can see, thanks, Jing. Do you want to elaborate from there?
Yeah, so I just want to add to that, if actually there's no link, we can see that the convergence doesn't exist, especially compared with what we actually would have observed.
Yep.
Okay. Yeah.
Thanks.
And feel free to just ask questions, anybody. I see Martin Tomko's got using the hand raise function, but feel free to anybody just to jump in.
Thanks for the great talk, and I'm trying to get my head around all of this. But I was wondering whether the method would be usable, so it's not just your package, but the method in general, assuming that we have a situation similar to what Yoshi mentioned, that we have X and Y's, or possibly a very large number of time series, where we assume they all depend on some Z, or maybe some of them depend on Z, some don't, and we just want to find out the grouping of those that belong together. Is that something that's possible? To me, it seems like some of the first exploratory stages of the method would be possible would allow you to find out those that sort of follow a similar pattern despite them being lagged or whatever.
You mean you want? So sorry, I'm trying to understand.
I'm trying to, let's say that I have a large amount of time series, and some of those I suspect that follow are the consequences of a similar causal effect. And I want to identify those that belong together and somehow isolate them from the rest. So they would have a similar. I would expect that they would belong closer in the same manifold.
Okay. So in some way you can think about X causes Y1, Y2, Y3. You have a bunch of those time series, right? But they may have the similar properties. And one possibility, you can cross map all the possible pairs. So that's say you have 100 time series. So you basically do a cross mapping of 100 squared, and then you will be able to plot the charts, actually the causal directions. And by doing some sort of a clustering, you will be able to find out the groups. That's probably you were referring to. Yeah.
Yes.
It's very computationally heavy though.
Possibly have thousands of time series over a very long period. So do you think that this method would probably not cope?
You generally get a few thousand, let's say a few thousand points in the time series. You do still do that in a few seconds on a single computer. And if you have access to more powerful ones, the largest test we run is actually with a time series more than 100,000 points, which is quite large.
I think I have 36 millions currently.
Okay, that goes to another magnitude. Yes, okay. So that would be a challenging computation like this.
So there's also I'm going to put in a link here. There's also a specific method that is implemented in the Stata package, and it's called co-prediction. And the idea is, all of these are related basically to the same kind of underlying theoretical framework or idea of reconstructing a manifold and then assessing its properties in order to make inferences about the relationship between different time series. So what you can do is, it's almost like a kind of network analysis, I guess, amongst the variables, right? So this co-prediction method, it uses the logic of simplex projection, and you're looking for dynamic similarity in the variables. So, so I provided a link there to both the documentation for the REDM package, which also does it. And then there's a paper there that exemplifies the method. And what they're doing is they're looking for relationships among different like fish species or something. But you can just think of those as different time series variables. And then the question that method, but as well as cross mapping, would answer is whether or not there's some kind of common underlying dynamical system that is right, that the time series are both reflecting. So even if they're uncorrelated in a linear sense, they could still be dynamically related, obviously.
Yeah, exactly.
Right, and so that method is implemented in our Stata package, and you can use that.
Where's the link?
In order to assess. In the chat. Oh, sorry. Hold on. Here it is.
Right, I forgot the co-predict options.
Sorry, what was it called? The
There it is. So now it's in the chat.
Co-prediction.
Yeah, and here's a paper that exemplifies it. So there's the documentation for some documentation online for it as well as this.
Okay. Thank you.
So that's just one way of doing it.
Yeah, so co-predict is one of the ways to examine whether the two time series share the same dynamics. And that's one of the ways to do it. Yeah, I actually forgot to mention that in the presentation. Yeah.
So it's obviously kind of an ongoing thing, right? The development of the package. So at least that paper that's available on Jingqing's the GitHub page. So this paper is available at the bottom of this GitHub page, the Stata paper, but that is, it doesn't actually describe all the options. The paper would have had to, it would need to be much longer to go into great detail. There's a lot that the Stata package can do. It can do basically everything the R package can do. It's just not, and the documentation is there in the help file, but here, actually, I can just provide the link to the paper as well.
The GitHub page doesn't work.
Hold on. Here we go.
There's a link to the PDF. I think that's probably.
Yeah. So here's the page and the PDF. Let me link to that too. Here we go.
So can I just double check though, Martin, that I'm just looking at your response to the clustering suggestion. So the cross mapping by itself is not like a scale-free kind of comparison of time series. So if there's, you'd still have to do, the delayed procedure, or this is my understanding anyway, you'd still have to do the delayed procedure or have some other kind of pre-processing of the data stream to identify, either a delayed dynamics or a dynamics that was happening at a different time scale that was influencing there might be one dynamics at one time scale, another dynamics at a different time scale.
Agreed. I was more referring to the distances between the points in time series, at least, freshes or whatever other, and how you start investigating the different options for different lags. So.
Right.
So okay. Similar dynamic time warp, it could do something as well, possibly, but it's I was looking at these non-parametrical options here.
Right, and as if it gets complicated, you will need to consider having a different distance metrics rather than a naive Euclidean distance used in the package. And adding on to the Simon things, actually, another possibility to explore is you cross-map all the possible lag values, and you just do it a lot more. It's like you brute force all the possible relationship, and then you do the cluster at the end. You will be able to review the delayed causalities there as well. You can group them by the time variables as well.
Right.
It's a brute force method, yeah.
But if you've only got, what did you say, 3 million, 36 million observations, it shouldn't be a problem.
Half hourly for a year for 6,000 units.
Yeah, I mean, I guess the other thing to say here too, right, is that it depends, what the relevant rate of change is and so forth. So, if it may be possible, for instance, to average over some time spans and not, I mean, you have to check because it could compromise the underlying dynamics depending, but it depends what time scale that dynamics is happening on relative to your sampling rate.
No idea. Yeah, I'm sure I don't have the cause, but I do have responses across a lot, and I want to find out those that respond in a similar way, but non-trivially.
I imagine one of the possibilities you sample the data, you don't actually need 36 million points. If you look at this chart from the Chicago crime ones, we have more than 4,000 points to do that. But actually things are quite stable by 1,000 points already.
Mm-hmm.
And this is, and if you look at this, the logistic map example, we probably only need about 50 to 100 points in order to get
I think I'll do something like that as well. I think there's strong subsets of data that would help.
In the paper too, this paper with Sugihara on it, I think they use a clustering method as a form of kind of secondary analysis to figure out which fish appear to kind of share common dynamics, or which species. Yeah, here on page 204. Figure 7.
Hold on, but which paper is it?
Sorry, so it's the article. This one. That.
Ah, the one. Okay.
Yeah. So you can say they're constructing. Got a dendrogram based on the co-prediction results. Page 204.
Doesn't want to download.
20 people are trying to download it right now.
Maybe.
Shouldn't actually matter.
There we go. Mm-hmm.
Right. So you're just getting a matrix of whatever it is, something that measures predictability. And so below the diagonal is one direction, above the diagonal is the other. And then, so it's not a correlation matrix, obviously, right? Because you get both above and below the diagonal because you can predict in both directions. So that's just an example. So I guess one of the takeaways is that, there are all kinds of really only partially explored opportunities for kind of taking results and using them for a variety of purposes, including in this case, clustering. Yeah. So there's a lot of low-hanging fruit, I suppose, for new research. Okay. Does anybody else have any questions? Should we let Jing Jing get back to his day? Thank you so much, and thank you to everybody for coming. Obviously, if you're local, it's 11 a.m. for you. If you're not, can see we've got at least one person from New York for whom it's, I guess, 10:10. Is that true, David? Thanks very much for coming. And so this talk will be uploaded to the QMNet YouTube channel, and materials will be. Can we make the slides available too on YouTube? Okay, great. Thank you so much, Jing Jing, and thank you everybody else. And we'll see you next time, and we'll be in touch announcing the next talk. Thanks, Jing Jing.
Thank you. Thank you. See you.
See ya.